Okay, folks, let's have some fun. We're going to look at section G here, Riemann sums, which I'm going to be honest, I hate this section. I think it's very tedious, it's very dry, it's a whole lot of technical algebra to prove some results that we kind of already saw in the core. Um, Technically, this is in the syllabus. If we take a look at the course guide and tilt our heads, we see right here that the integral being a limit of a sum, specifically a lower and upper Riemann sums. We'll talk about what that means in a moment. But we'll see that is in the syllabus. As of recording this video, I don't think there's ever been a question specifically tied to this, but that doesn't mean that it couldn't pop up. And we will reference some techniques in this video that are important for some other, they connect well to other topics that have come up in a number of cases. So let's go. And what I'm going to do is really just, I've copied like every single piece from the textbook, and I want to read through it and talk about what all the symbols mean. And this is not to insult your intelligence. The first time I read through this section, I had to really stop and read it 2 or 3 times to make sure I knew what all the variables and subscripts and everything stood for. So let's go. We've got some curve, f of x. There's an area underneath the curve, which we're calling capital A, and we're only looking in between 2 particular x values called a and b. What we're going to do is we're going to partition the interval. So we're going to break it up into sub-intervals, starting at A, which is going to be x sub 0, and then the next sub-interval might be here. We'll call that x sub 1, and then the next one might be out here. That could be x sub 2, and the next one could be here. That would be x sub 3. So the sub-intervals just go kind of wherever we want them to go, all the way to b. And however many sub-intervals, we'll make n sub-intervals. So the last one will be x sub n. The first one was x sub 0. Let's see that. Okay, that's a little better picture than what I drew. Great. The length, the horizontal length of any particular subinterval. So here we're calling it the ith subinterval, and that's the subinterval going from x sub I minus 1 to x sub I. That distance is always just x sub I minus x sub I minus 1. Again, like imagine like that there's actual numbers here for just a minute. Like if I was looking at the area from 4 to, I don't know, 9, and maybe this point here, maybe x sub 1 is 5 and x sub 2 is 6.5. What's the length of that subinterval? It's 1.5, right? Because I did x sub 2, 6.5, minus x sub 1, or 5. That's all that's saying up there. But we're going to try to keep it general here, so no numbers. We're then going to take any particular x value within a subinterval, and we're denoting that as x sub I star. So that's in the ith subinterval. It's arbitrarily chosen. It could be any value in the subinterval. And then we're going to make a rectangle. So I don't know, let's say we were in here. Let's choose that point as my x sub 1 star, because that's in the first subinterval. I'm now going to make a rectangle whose base is exactly equal to this width of the subinterval, and whose height is equal to the value of the function at x sub 1 star. So wherever that arbitrary x value was, I go up and I find a height. So I'm going to make a rectangle at exactly that height, at exactly the width of this subinterval. So then maybe that will look like this. And we can see that in this case, to the left of that dotted line, my rectangle is a little bit above the curve. To the right of the dotted line, my rectangle is quite a bit below the curve. I'm going to use this rectangle to estimate the area under the curve. It's not going to be perfect, but it's an estimate, okay? And that's what we see down at the bottom. So our estimate of the area in each particular subinterval is just the height of that rectangle times the base of that rectangle. Here is the illustration from the book. They did one for the second subinterval. So they've got x sub 2 star right here. they've got f of x sub 2 star right there. So this particular area, a sub 2, would be equal to x2 minus x1 multiplied by f of x2 star. Anyway, we do this for every single one of our n subintervals, and then we add together each of these areas. That's what's happening here, and that is an approximation for the total actual area A. And this is, again, this is the product for the first rectangle all the way to the nth rectangle, and we can write this entire thing in sigma notation as such. And this is called a Riemann sum, named after German mathematician Bernhard Riemann. He did a lot of fancy math back in the day, famous guy. Okay, now this was all like totally arbitrary, so our intervals are of any length, and the point that we're choosing in the subinterval is literally any point. I'm going to show you some special type of Riemann sums next, because there's a lot of different types. And look, you've done core calculus before, so you already know that this is going towards the definite integral. So here's some images that I got, I think from Wolfram Alpha. I forget what website I was playing around on. Anyhow, here, this is one way that we could approximate the area under this curve. It's with what is called lower rectangles. Each of the rectangles that I drew here, sorry, you probably don't like all that stuff there. Each of the rectangles that I drew here are all below the curve. So in each subinterval, the height was the lowest part of the curve inside of that subinterval. So my x sub I star is not being arbitrarily chosen anymore. It was chosen to be the point which has the lowest point on the curve within that subinterval. We can compare that down below to the upper rectangles, which is just the opposite. Now every single rectangle is drawn to be above the curve. Certainly, this is going to overestimate the area, and this is going to underestimate the area. There are other ways that we could create our Riemann sums. AP Calculus teaches left rectangles and right rectangles. And you can see that the left rectangles, they just touch the curve at the left end of each subinterval, whereas the right rectangles touch the curve at the right end of each subinterval. Left and right rectangles are going to over or estimate the area depending upon whether the function is increasing or decreasing. And then we've also got midpoint rectangles. So you can just make your rectangle height for the middle of your rectangle. You can just make your x sub I star right in the center of the subinterval. And there's other things you can do. You can use trapezoids. AP Calculus does that. You can use Simpson's rule is another thing. I don't believe AP does that. Maybe BC does. It's been a while, sorry. What we're going to do in IB, as we saw earlier on the syllabus, is only lower and upper Riemann sums. So lower and upper rectangles. This one or this one. And here's what the book has to say about that. This is going to be all about our lower rectangles. This is going to be all about our upper rectangles. So we're choosing our x sub I star so that its associated y value is the minimum value within its subinterval. It's called a lower Riemann sum, and we're going to use L sub n, L for, lower, not L for left. Don't confuse it with the AP rectangles. L is for lower, and we have its associated sigma notation. And then we also have the same thing down below. If we choose our x sub I stars so that their y values are the maximum within the subinterval, then we're going to have u sub n. And the formulas look the same. The delta x sub I at the end should be the same for each of them, because we could build these using the same subintervals. It's just the part right here, so the f of x sub I star, that's going to be different for each of these. The next thing we're going to do to make it a little bit easier to calculate these is we're going to decide to make our subintervals all the exact same length. So no more arbitrary x values. If I want to have 10 subintervals, I'm going to take the total length from A to B, divide it by 10, and I'm going to make a subinterval where I need to. In this case, now delta x is always going to be equal to b minus a divided by n. That's kind of what I just said. Take the total distance from b to a, divide it by how many rectangles, how many subintervals you want to have. That's going to be your delta x for every single time. For choosing x sub I, let's think about this. There's a lot going on there, right? Well, let's use this formula. What's x sub 0? We said before that x sub 0 should be a. Is that what I'll get out of this? Yeah, because then that I would be a 0, that term would drop out, and then I'd be left with just a. If I wanted to try x sub n, okay, well, when this is an n, those are going to cancel out, and then my a's are going to cancel out, and then I'll just have b. So that makes sense. So this gives me a general formula for finding any particular x sub n, and that makes sense because I'm just starting at the very first, the left endpoint of the interval, and then I am adding one length, one unit of the of delta x for every I. So when I is 1, I'm adding one of those to a. When I is 2, I'm adding 2 of these to a, and so on. So that, I probably talked longer about that than I needed to. And then the Riemann sum is therefore going to be equal to this. Why is that? Well, remember that the way we saw it written on the previous page, we had like a delta x over here on the right-hand side, but that is just being rewritten there. And that we're able to take that out of this summation because there's no I in that anymore, because it's the same for every single x, x sub I. So since that has nothing to do with I, and that's the variable that's actually happening in the, changing in the sigma, we can just take it outside and multiply at the very end. And then finally, if we're going to evaluate some Riemann sums, there are a few shortcuts, some of which we should definitely know. This first one should be obvious. The sum of c, as I varies from 1 to n, is just c times n, because it's equal to c when I is 1, and then it's equal to c when I is 2, and then it's equal to c when I is 3, and so on and so on. How many c's are there? There's n c's in that summation. The second one we should also know, because this is literally just asking us for 1 plus 2 plus 3 plus all the way to n. That's just an arithmetic sequence. So that's something from the core. So we should be able to calculate that series using formulas from the formula book. It's that. The third one, okay, this is more challenging, and I don't expect any of you to just happen to know this. There's no reason to. Again, this is asking us for what's the sum of squares. Well, okay, it's 2n cubed plus 3n squared plus n over 6. There it is. We're going to use that in a minute, so maybe jot it down. But there's no reason for you to necessarily know that. And if you had to use that to answer a problem, then you would be either given it, or you'd be asked to show it somehow, or you might be asked to prove something by induction as a first part, although I doubt that you'd see induction on paper 3, because that would be a lot of points dedicated to it on a paper that's already pretty short. So the plan here is as follows. First of all, as I said earlier, the sum of the areas of the lower rectangles has to be less than the actual area. Likewise, the sum of the areas of the upper rectangles has to be greater than the actual area. Also, I think it should stand to reason that the more the more rectangles that we have, the more accurate our estimation will be. I apologize, this visual is going to use left rectangles instead of lower or upper, but the principle is the exact same, I assure you. So here I have currently. Let's make this smaller. Okay, we got a right rectangle, excuse me, a left rectangle with one rectangle. That area is not a very good estimate for the area entirely underneath this curve. I make more rectangles. We're getting kind of closer. Maybe it almost starts to look like it now. And we see as I really pump up these rectangles, as the limit of the number of rectangles approaches infinity, the sum of their areas is approaching the actual area underneath the curve. And it's the same idea for lower sums and for upper sums. So now we tie this back to the squeeze theorem. And so this page mostly is just repeating what I said before, but I want to focus right down here. So because the area A is squeezed in between the lower and the upper rectangle sums, the lower and the upper Riemann sums, if I could prove that the limit of the lower areas is the exact same value as the limit of the upper areas, then I'll know what the actual area is. So that's what we're going to do with a whole lot of, quite frankly, ugly algebra. Let's do one. And this is just a simple function. This is x squared on the interval from 0 to 1. Okay, part A. We're going to just make the partition. We're going to do this into n subintervals. Okay, so this total distance here from 0 to 1 is 1. We're going to make n subintervals there. Figure out how wide they each have to be, and write x sub I. Okay, well, using the formula from before, it would be b minus a over n, or just 1 over n. Does that make sense? Right? Like each of these regular subintervals, because they're all to be the exact same width, they should all be 1 over n. That's obvious. What are my x sub I values going to be? The first x sub I value is just 0. That x sub 0 is 0. X sub 1 is going to be my first value, 0, plus 1 of these distances. So that'll be 1 over n. My next one, x sub 2, is going to be my first term, 0 plus 2 of those. So that'll be 2 over n. And 3 over n all the way up to n over n will be my nth, my nth term, x sub n. Okay, so far so good. I think that's pretty obvious. So anyway, x sub I, as we have written down here, x sub I is going to be I over n. All right. Part B and C, we're going to show that the lower and upper sums can be found using these expressions. Notice they're almost the same thing. Really, it's just those signs are different. Anyhow, let's do it. So here's our work for B. What is and C, excuse me. So what's happening here? Well, the minimum value in this particular case, because we're dealing with y equals x squared, and x squared, I know from 0 to 1, is always increasing. So that means that the minimum value is always going to be at the left-hand side of the subinterval. So in this case, the lower rectangles, it's the same as doing left-handed rectangles, like the AP would do. So we're using little m to indicate minimum, and that's going to be associated with x sub I minus 1. That's the left endpoint of the subinterval. Putting that into the formula, because remember y is equal to x squared here. So when squaring x sub I minus 1, using the formula from the last page, remember that x sub I is equal to I over n. That means x sub I minus 1 is equal to I minus 1 over n. So we're going to square that, and that's going to be its associated y value. So now the associated Riemann sum for that's going to be, first term here, this is my b minus a over n, 1 over n, that's the width of each interval, times, and then we're going to do the heights of each interval. So that's what we got going on here. And then we're just going to do some algebra. Notice we can take this n squared out because that has nothing to do with I. So now we have 1 over n cubed on the outside. And now we have to deal with 1 minus I I minus 1 squared. And then I think there's a few different ways we can approach this. 2 different ways we can approach this. I think my first thought at this point would be to say this is 1/3 times the sum of I squared minus 2I plus 1. And then you can then break that into 1/3 times the sum of I squared plus the sum of, or minus, excuse me, the sum of 2I plus the sum of 1. And I think that should work. But a neat trick that the book pulls without really explaining too much is you'll notice that instead of I minus 1, we just have I. But also, look carefully, this 1 changed to a 0, and this n changed to an n minus 1. So what's going on there? Well, let's look at that first summation. When I is 1, what do we get out of that? Well, we get 0. When I is 2, we get 2 minus 1, so that's 1 squared. When I is 3, we get 3 minus 1, so that's 2 squared. All the way up to when I is n, we get n minus 1 squared. We can get that same exact sequence out of this one. When I is 0, we get 0. When I is 1, we get 1 squared. When I is 2, we get 2 squared. All the way to n minus 1. Put it in, we get n minus 1 squared. So that just, it simplifies things quite a lot. But you don't have to identify that shortcut, but it's nice if you do. Anyway, then what's the sum of I squared? Well, we saw that on the previous page. We were given a formula for that. So we might have something like that. And then we just do a little bit of algebra to simplify that down to there. Okay, great. Now we do the same thing on the right-hand side. Are you loving this right now? Oh my gosh. Okay, so the maximum value, we're going to call it capital M. That x value is going to have to be at the right end of the subinterval, since we have an increasing function. So that'll be x sub I. And then in here, instead of I minus 1, we'll just have I over n squared. Okay, wonderful. Calculating the sum now, we still have a 1 over n on the outside, because that's the width of each rectangle. And then the inside is just going to be the sum of I squared over n squared. Once again, this n squared comes out. And then we got 1 over n cubed times the sum from 1 to n of I squared. In the last one, it was from 0 to n minus 1. This time it's from 1 to n. Oh, I'm sorry. I should have referenced that before. Let's go back for just a moment. Where did we have those? The shortcut we were given was from 1 to n. So that actually works perfectly for letter C, because that's from 1 to n. For letter B, yeah, how would we have gotten that? Let's talk about that. So the way we would work this out is we know what the formula is from I equals 1 to n. Now that particular series has, when I compare it to this one, it has one extra term, doesn't it? It has the term when I is equal to n. So I want to remove that term. And there's nothing, this is not official notation, I'm making this up. This just means I'm removing the term when I is equal to n. But also, it's actually missing a term also. If I look at the bottom, this series is starting with 1, but the series over here is starting with 0. So I want to then include the term when I is equal to 0. So when I is equal to n, in this case, that's just going to be n squared. So I'm going to subtract an n squared. And then when I is equal to 0, well, that ends up just being 0. So I need to subtract an n squared. Let's see if that works. Over here, that is the sum from 1 to n. If I then subtract and n squared. Oh, but I need to have it give it the same denominator, so I'll make that 6 over 6. Oh yeah, then you know what? 3n squared minus 6n squared, that does give me minus 3n squared. So that's how I could use the formula in that one. So I'm sorry that I skipped over that at first. I did not mean to. Anyway, we have successfully now shown that the lower and Riemann sums are given by the expressions as required, and from here it's smooth sailing out of here. So hence find the area under the curve and above the x-axis. All right, well, as we said, that area has to be bounded in between the areas of the lower and upper rectangles. So we've got that right there. And then we're just going to take the limit as n approaches infinity. The more rectangles we have, the closer to the actual area we'll get. But when n approaches infinity, this term and this term and this term and this term are all 0, leaving us with exactly 1/3 on both the left and far right-hand sides of this. So the actual value of A, our area, is squeezed in between that 1/3 and 1/3, and it must be equal to 1/3 units squared. That was very long for something that amounted to solving this integral, which should take us only a matter of seconds. But this is what the option topic is all about in HL Math. Gotta love it. I'm not going to do these other 3 examples. These are the only 3, like homework problems or whatever in the textbook. They all work the exact same way, and all the work solutions are in the back of the book. So check those out. Notice that in each of these cases, it's a monotonically increasing function. Sine of x from 0 to pi, increasing. 2x, always increasing. X squared from 1 to 2, increasing. If we had had a decreasing function, then the change we'd have to make, if we were decreasing on some interval, if this is x sub I minus 1 and this is x sub I, well, now all of a sudden the lower rectangles are being formed at x sub I, whereas the upper rectangles are being formed at x sub I minus 1. That's the only change. What would happen if we had a function that was both increasing and decreasing on an interval? Well, this is terrible then, because now we have to. This is why I think this topic doesn't really show up in the IB, or if it does, it's going to be something really simple, like one of these 3 in front of you. Because now, like, depending on which part of the interval you're in, the upper rectangle might be the right endpoint, or it might be the left endpoint. And oh, by the way, if your interval has the maximum point in it, then your upper rectangle is going to have to be formed, like around that. And so that's not x sub I or x sub I minus 1. So my hunch is that if a problem like this were to show up on an IB exam, it would have to be, as I said, first of all, a very simple function algebraically, because we need to be able to work with the expressions for delta x and for x sub I. So it's going to have to be something easy, like just squaring stuff or multiplying by 2. Even here isn't too bad because of the particular partitions that you're told to use. And it's going to have to be something that's monotonically increasing or decreasing. And okay, look, the rest of the section just kind of ties this together with definite integrals. I don't really want to labor on this any longer than I already have. The definite integral is equal to a limit of Riemann sums. Hopefully you can kind of see their connections. We've got, the integrals going from a to b, which were the endpoints of our interval. When we calculate a definite integral, we know we're putting in b and then putting in a and subtracting, so that's kind of related to what we see there. We've got the summation, which has got a sigma is kind of turning into this elongated s of the integral symbol. They're the same thing. I don't have anything else to talk about here. Other point of interest down below, if a function is continuous, then it is integrable. We can we can integrate the function. Now that is not the case for differentiation. If it's differentiable, then it is continuous, and if it is continuous, then it is integrable. So if we can differentiate a function, we can always integrate the function. But that's not necessarily true the other way around. And the final thing that we see in this section, something that I believe you've seen before. I know you've seen before. This is straight from the core calculus. If our function is all above the x-axis, then great. The definite integral, as defined, is equal to exactly the area. If the function was underneath the x-axis, we'd be getting an area which is positive, because I mean, when we think about area is always positive. But in this case, the definite integral would be the negative of that area. So when we deal with calculus, we are thinking about signed areas, which was really helpful back in the core in terms of like applications to kinematics and whatever else. So there's that. Okay, so what were the major points from this video, which is pretty lengthy considering I did exactly one problem. First, the area is squeezed between the lower rectangles areas and the upper rectangles areas, and that, again, this is going to be something that's going to come up later on in the option topic, so that's super, super important. And the rest of it is just, you know, algebra. I'm not going to sit here and tell you that you need to, you know, that you need to memorize all those summation formulas and the notation and the setup for the Riemann sum, because again, it hasn't happened on any exams that I'm aware of. If you're watching this video next year, perhaps my perspective will have changed and I'll let you know. But yeah, so I can promise you I'm not going to include any of this on a major assessment of mine, because I don't think it will be on a major assessment given to you by the IB. That being said, here it is. You've been warned. You should know it when exam time comes. Okay? I'm going to leave it there. I think this video hurt me enough to make. It probably hurt you to watch. So we're gonna say goodbye now. Goodbye!